Welcome to this talk. I'm going to be talking about site reliability engineering, and I guess this talk is a little bit half a philosophy talk in that how I think SRE sort of what it means and what it should be and how we should be trying to do it. But don't worry, there's a bunch of actual practical stuff in here. It is not only philosophy. So a little bit about me. Actually, first I should acknowledge this is the after lunch slot. This is always the slot that's most difficult on any conference, and I think on the day when Donald Trump has just been re-elected, it may be more difficult still. So thank you all for being here on this very, very, very strange day. So about me, I'm a beekeeper. I do keep bees. This is a photo of one of my hives. I live in Ireland, as I mentioned. Bees are complex systems, so this actually sort of does play into what I'm talking about a little bit. I've been a contributor to several books about site reliability engineering, including the first one, the Google Production Systems one, and some others. And I have spoken at other conferences like InfoQ and Øredev, SREcon, which is sort of my home conference. I'm one of the organizers as well. I'm currently working independently. I've previously worked at Slack and at Google and some other companies that you won't have heard of as much. But yeah, I'm currently doing independent work, so I'm available for consulting about things like doing production readiness reviews or applying systems thinking to your strategy in your organization. But mostly what I'm doing is I'm doing research on how we do troubleshooting as software engineers, as systems administrators. I'm doing that with Lund University, only up the road. So it's great to be here in Malmo for this conference for that reason. So, yeah. Who here has ever had a site reliability engineer job title or has one now? Okay, like 3 people, and some people who are not sure. Okay, cool, interesting. So this is going to be just to know where to pitch this as an audience. So this is Niall Murphy, who wrote this book, Site Reliability Engineering, which really was sort of when SRE started to come out in industry, and then, you know, organizational leaders started to do horrible things like point at teams of perfectly nice sysadmins and say, "You are now SREs, and we expect much more from you." This thing started to happen. So this is Niall ripping up his own book and declaring SRE kind of dead. So yeah, there's that. Is it dead? I don't agree. Niall thinks that there's sort of no philosophy of SRE and that it's just a sort of a fragmented mess. I think that there is actually an underlying, quite principled systems approach that I've seen the very best SREs do, and I think that this can bubble up to the fore and sort of become the philosophy of SRE. So, identity crisis, total identity crisis. SRE originates from Google, where Ben Traynor, who was in charge of sort of ads reliability at the time, said that SRE is what you get when you ask software engineers to do operations. But then, a couple of years ago, he decided SRE wasn't as good anymore, and he said, well, actually, SRE isn't operations. So is it even operations? Nobody is sure. I think it is operations, and I think there is no shame in operations. We need operations, and it's a very big percentage of the software lifecycle, and it's also where, to my mind, many of the most interesting challenges of software lie, and something I've dedicated a bunch of my career to. So, you know, is it just holding the pager? Do I have to have SLOs? Am I not an SRE if I don't have SLOs? All of these things. SLOs, by the way, are service level objectives for anyone who hasn't been an SRE-inated yet. So yeah. So we have, if you could go out and you Google like what is SRE, what are the pillars or the tenets of SRE, you get a bunch of, you know, stuff like this, and it's all fairly fragmented. I mean, it's, you know, there's no kind of North Star. There's no unifying kind of theme or concept here. It's just like a shopping bag of stuff. That's not a philosophy. That doesn't help you sort of make choices. It doesn't help you have a strategy. It doesn't help you, you know, figure out what the best approaches are. It's just like, well, you must do this, and you must do this, and you must do this, and you must do this. And hands up here if you have too many things to do already. Yep, yeah, that's a lot more of you than our SREs. So I was at a talk by Andrew Clay Schaefer, who's one of the so-called fathers of DevOps a couple of years back, and he said that he talks about superficial practices, about ritual without reason. And I think if you're just adopting practices because somebody put them on a list of pillars, then that's what you're doing. It's empty. This is empty. This is not a profession. So the pillars of SRE, is it just some poor schmuck being crushed under the weight of a bazillion YAML files and HashiCorp config language scripts? Or, well, not really scripts, configs. Maybe. But that's not a very happy thought for our profession either, and this is not a philosophy either. So I think if we say that things like observability and incident management are the pillars of SRE, it's like saying that wood and glass and concrete are the pillars of architecture. They are not. They are materials that architects use. It's mistaking the sort of the tools for the essence of the task. You know, architecture is not about the materials. It's about making structures that serve a purpose, as workplaces or as public spaces. And, you know, maybe sometimes it's just for showing off. I mean, we have Kubernetes and service meshes and things for that as well. So, this came from my work Slack at the time. We were talking about pillars of SRE, and you know, I don't take this stuff very seriously. So I said, obviously, that you know, SRE would go for the classical Roman good taste pillars, but yeah, obviously, the people started throwing shade at DevOps because, you know, clearly they would have the less good Egyptian pillars. That's not right. DevOps, contrary-wise to SRE, has got a really coherent philosophy. DevOps is absolutely beating SRE into the ground in terms of having a good philosophy. So, and I am simplifying things here because I have one slide and there are entire books. You could do a whole day workshop about this. But it's got a very clean philosophy. It's taken from lean manufacturing as practiced in Toyota and places like that. And so it's all about theory of constraints. It's about continuous improvement, or Kaizen. It's about eliminating bottlenecks and friction. You know, this is why there's this huge emphasis on being able to deliver rapidly and safely to production. The idea here is that being able to do that, it unlocks all sorts of great things, like the ability to, like in operations, it helps us because we're not dealing with bad rollouts all the time. And if we do have an incident, it means that we can confidently and quickly roll out. So, you know, it helps, you know, having good CI that has a fast, reliable suite of tests that you can trust. That's why that's become such an underpinning of DevOps, because they believe it, and I think they're right, that it does unlock a lot of really useful stuff. This is a philosophy, not a set of pillars, because it lets you prioritize work and make choices. So if you're working in a DevOps role and you know, you're wondering what is the next best thing to do, you ask, what is the biggest source of friction? What is stopping me from being able to, you know, iterate quickly right now? And that gives you a North Star that you can work on. That's great. Now, a lot of people say that SRE is an implementation of DevOps, and that is something I massively disagree with. And back years and years ago, before I left Google, I was actually on the, Google has an internal body called the SRE brand team, and the whole idea of this body was to sort of use SRE as a brand to promote cloud and stuff, and to try and give it a coherent identity. And one of the other people on this team coined this SRE as an implementation of DevOps phrase. And the reason that I disagree with that is because I think the philosophies that kind of underlie them are very different, even though we haven't very well articulated the SRE philosophy. So DevOps is sort of taking the developer experience as central. The DevOps centralizes that, and it's all about making the developers fast and productive so the organization can roll out features and survive. And it's sort of classically, I guess, more associated with smaller to medium organizations who do exist to move fast. But SRE really originated in another set of organizations that already had very large-scale, complex, profitable systems that were printing them money. So I'm thinking specifically here of organizations like Google Ads, but also some of the other hyperscalers have the same problems in that they have this big money machine and they don't need to roll out a bunch of features super fast, but they do need that machine to keep printing money. and for customers to trust it. So you've kind of got a slightly different set of problems here. In the SRE model, we have always tended to, at least the way, my path through it, we've always really centralized production. So instead of centralizing, can my developers move fast and effectively, we centralize the idea of is production stable? Is it going to be able to keep scaling? Do we have any sort of ticking time bombs here that are waiting to go off and blow up my production? Do I understand my production? Do I have enough monitoring? Is my alerting good? That's why SRE is traditionally sort of focused on that end of things. So I think they're complementary approaches because, like I say, I feel like, in one hand, you're very focused on what are the developers doing and experiencing, and on the other hand, you're focused on production. And I think a lot of organizations sort of conflate the two things, but I think you do well to think about which of these you need the most, and maybe you need both, and they're complementary and can work together. So, but they're not the same thing, not in my view. So what is the SRE philosophy? Well, according to the Niall Murphy of SRE book fame, it is a donut hole in a donut hole, and the hole is not at the periphery, but at the center. Paraphrasing Benoit Blanc in Knives Out. But going back to the basics, we know that in SRE we have some practices that are standardizable. And what I mean by a standardizable practice is, it's something that's systematizable that you could build a product to do, that you can do this in any organization. So if I'm coming in as, a salesperson for a company that's building service level objective tooling, I can come into your company and say, oh, okay, well, you will need some service level objectives. Oh, look at this, you have latency, you have errors. Great, we'll set an error budget, we'll plug you into my system, and look, now you have service level objectives that you can talk about in your meetings, and now you can have alerting based on this, and this is great. You can do this more or less anywhere. And there are system-specific nuances of service level objectives, but that's not the talk for today. Incident management is, who here is using some sort of tooling for managing software incidents and outages, like incident.io or Jelly or something like that? Nobody. Oh, okay, a few people. But this is an aspect, so incident command is something that sort of comes from SRE, I think more so than DevOps, although both of them have borrowed it from a thing called high reliability organization theory. And I could give a whole talk about that. It's really cool, but I won't. But the whole idea here is it's about bringing together a temporary organization to manage something that needs managing in the short term. So it could be a security incident, could be a production incident, could be doing a risky rollout. It could be a lot of things. But again, this is something that is it's not system specific. It's something you can bring into any organization, and you can build products that do this, and many people have. And then some kinds of automation are similar as well. So you've got things like temporal that do long-running automation for you, and so on. But there is a lot of work that is not standardizable. And I've classified this as SRE work, but the reality is there are a lot of people who wear job titles like DevOps, or job titles like sysadmin, or job titles like software engineer that are, and probably others I'm not even thinking of, that do this work. This work is all system specific. How you do this depends on the details of what you have and what you've built, and also the details of your organization as well, its structure and how it works. I cannot build you a product that will do these things for you, or even that's going to take you very far down the road of doing these things. They're context specific. They're not systematizable in that same way. Like system design and improvement work, this could be absolutely anything. This could be saying, well, we're having too many security incidents because people are spinning up services and not locking them down properly from the public internet, and therefore we will build a new platform that will do this, and people won't have to configure ones individually. That's an example of this. It could be redesigning a data pipeline to be reliably multi-homed. It could be introducing different classifications of requests in your system and implementing prioritized load shedding. It could be anything like that. Your monitoring and alerting might just be very standard kind of golden signals, latency and error rate. But in many cases, we have system-specific kinds of things like correctness, or freshness, and things like that that we would need to worry about. How do you manage your load balancers and your databases? That's a lot more than just error rate. So things get a lot more complicated. Disaster testing, to do that well, you have to think about, what do I actually intend my system to survive? If you've built your systems on the understanding that you run them in US East 1, and if US East 1 goes down, and you all just go to the pub and wait until it comes back, I mean, that's actually a perfectly viable thing that many organizations have done. They've just said that we're not designing for this particular AWS region to go down. We are homed here, and if it goes away, then we go away for the duration. And actually, a lot of companies get away with that because their customers are there too. But when you do your disaster testing, you have to take that sort of thing into account. There's no point testing for things that you don't intend to survive. But conversely, you do want to test the things that you think your systems ought to be able to tolerate, but only you know what those are. You can do off-the-shelf chaos testing, where it will do things like interfere with latency and interfere with error rates, partition your systems, this kind of stuff, restart things. That's fine, it gets you so far, but it doesn't get you into the application-specific risks. So things like if you're using a multi-home system, what if one half of it goes away, or things like that. So you need to do some system-specific design work here. So the most effective SREs that I have ever worked with, they tend to lean very heavily towards this kind of work, and that's where they make their impact. They don't make their impact by running around all the time just implementing SLOs. They do a lot of work that is system-specific. You need to engage with your systems deeply and over a long period of time to be effective at this. This is work where you can't just parachute into a team, take a quick look and say, okay, right, well, I'm going to fix this major part of your service. You have to really spend some time observing the system, understanding it, its dynamics, and what's going on. So my thesis is this is our strength and this is what we should be aiming to be good at rather than building 1,000 more incident management tools. So my philosophy of SRE is it's about understanding complex systems and making appropriate interventions to make them better. Am I just restating engineering here? Not quite, because we're not talking about building features, all these things. We're talking about thinking about our systems at the level of the system. And that means not just this service or this service, but also looking at how everything functions together to achieve your organization's goals. This is where I think SRE in particular tends to shine, because you tend to, in an organization, have one or a small number of SRE teams and a larger number of developer teams. So this is a place where you can observe the interactions between teams and between services and find these kinds of systemic interaction problems. For example, at a company I worked at, we were having these intermittent weird errors where suddenly, for a little while, services would start graying out and returning a lot of errors to their clients. And eventually we figured it out that the team that ran one of the platforms, they kind of said, okay, our developers want fast rollouts. We'll make the rollouts super, super, super fast. And so developers love this. Okay, great. I click the button, my rollout's done. I can go and be done with my day. But they had made it so fast that the load balancers and all the sort of the client architecture were still caching all of the old DNS results or the other service discovery mechanisms that were being used, and therefore they didn't know where any of the new hosts were to connect to them. So the rollouts were so fast they were outpacing the load balancing and the service discovery architecture. So we kind of went, okay, we need to make this work better for the whole organization, not just this one kind of KPI of very fast rollouts. There is a limit on this, and the limit is the rest of the systems involved. So some examples of what I consider good kind of SRE technical systems interventions. So after some research, it's been pretty well determined. And I like this one because this tends to apply across any kind of system where you have replicated data, multiple copies of data residing in different machines, and you have a system that it could be a file system, could be a database system that is responsible for making sure that you always have or aim to have a certain number of copies of your data. So we have lots of systems like this. But what seems to be kind of universally true for them is that hosts go away, and then they probably come back. Sometimes a whole rack of hosts go away, and usually come back. So some of the sort of wisdom that's been gained from running these kinds of systems over the years is that rather than immediately re-replicating data from a host in one of these systems that has temporarily gone away, you should wait a while. And that's usually like somewhere between 10 minutes and an hour or so. This doesn't greatly increase your risk of losing your data because you still have other copies of it. But what it does do is it makes the systems much more stable if you have a situation where you suddenly lose a whole rack of machines because probably somebody has just rebooted that switch or it's lost power temporarily and probably it's coming back, as happens in 99% of these cases. So rather than taxing the system as a whole by eating a whole bunch of bandwidth, re-replicating as fast as possible, it's best to actually just leave it be, and only if these things don't come back within a period of time, do your re-replication. Another one, the cellular design pattern. This is something that has come out of, there's a really good paper a couple of years back by Mark Brooker and some others. It's called Algolia, and it has a long subtitle. But this is how they build a bunch of the storage systems at Amazon. So instead of having one giant system that all works together, what they have is a bunch of cells, and each cell is a complete vertical stack. So it's got storage, it's got management of that storage, and then you have something that load balances in and balances things between the different shards or cells. I like this as a systemic sort of intervention. You can make your systems cellular. It's quite hard after you've originally built them, but if you're building, complex infrastructure, it's worth thinking about early on because it unlocks all these systemic things that you can do. You have built-in isolation between your cells, which means that I think anyone who's run complicated infrastructure that's holding data knows that doing rollout safely is one of the most challenging things. This gives you a way where you can roll out with confidence to your dev shards, your dog food shards, and you can monitor that. So it's a really powerful sort of systems pattern. This is a small one, but this is something that comes up again and again, another kind of pattern. It's very common. You have counters. So a counter could be, system uptime type counter, and you have a counter that will count up and up and up and up, and eventually that counter will hit the maximum storage for whatever data type you're storing it in, and it will wrap around. It is very common for havoc to ensue at that point. So I don't know if anyone read the Orange site, Hacker News? Yeah, about 3 years ago they had both of their redundant servers die because of an issue like this. I think it was to do with their disks, actually, in their RAID array. They lost a bunch of them around the same time because they bought them at the same time, and they had these kinds of incrementing counters. They hit maxint, and oops, everything is gone now. So a little systemic intervention you can do is you can start those counters at like minus 5,000, and then your testers will see them roll over, and you won't have this problem anymore. So I think as we go through life and go through our careers, we sort of develop like a whole library of these kinds of patterns and system interventions in our head, and we can often reuse them in different scenarios. And this is quite a useful thing to do. But we also have social systems because, the software lives in the machines, but we manage the software and we are not machines. We live in organizations, and we have colleagues and managers, and we have office politics, and we have people who want to go home and sleep, and all of these human things. So we have a bunch of social systems interventions around this as well. So one example would be, how big should your on-call team be? If you have a very, very tiny on-call rotation size, you can be cheap and you can have your on-call rotation staffed, but you will have bad effects over time. People will burn out and they will leave and go somewhere else. Like, your on-call people are not slaves, they have options. So one of the sort of important SRE systems, or sort of social systems interventions, is to make sure that you have enough people in your on-call rotation so that doesn't happen. And that can mean things like sharing on-call rotations with other teams. It can mean things like including developers in on-call rotations, stuff like that. But there's also a sort of a second level of this, which is your on-call team should not be too large. Because if your on-call team is too large, then people start to forget things. And they start to lose confidence because they go, oh, I haven't been on call for 2 months. So it turns out that being on call for about a week in every 6 or 7 weeks seems to be optimal for this. SLOs and error budgets. I said that these were a tool and not a philosophy, and it's true, but they are useful for providing that sort of feedback loop, and that's as much of a social systems intervention as it is a technical intervention, because the idea here is to build structures where you're actually reviewing your SLOs and you're using that when you are prioritizing work and making decisions. Then blameless incident reviews. These are a social systems thing, because it's been discovered over time in many, many organizations that if I run incident reviews where I say, well, it was John's fault, he made the bad change and he should have known better, then you will end up with a bunch of negative effects in your organization, in that nobody will want to talk about what they were thinking when they made that change. So it's harder to fix whatever underlying problems may exist in your code base, the sharp edges. Also, nobody will want to make any changes, particularly any risky changes. So your organization will move slower. So this is why we want blameless incident reviews. It's a social systems engineering intervention to make our organizations more transparent, more willing to fix systemic problems and look at systemic problems, and to make the organization move faster. And automating toil is important because anyone who's worked in a big system that's scaling up knows that over time your toil tends to increase. So toil is sort of housekeeping tasks like provisioning new users, taking the backups, all this kind of stuff. It grows over time. So this is why we have to automate, because otherwise your team eventually gets overwhelmed if your project is successful. So this is all about thinking about how our socio-technical systems can be sustainable and reliable over long term. So systems thinking is in the title of this talk, so we should now talk about that. Systems thinking is a discipline outside of software, which is basically all about understanding and optimizing complex systems. And I think this is actually what we're doing in SRE in many cases without calling it such. I think it's a large part of the engineering part of what we do. And the core of it is about thinking of systems as entire systems. Not just saying, well, for the sake of this one service, we must move faster, without thinking about the impact of that on the rest of the systems in your organization and the people as well. I'm presenting quite a lot of the rest of this material from this talk, from this book, which is Stanton and Salmon's and so forth, many authors, Handbook of Systems Thinking Methods. They set out to actually make it useful to engineers rather than only academics, which a lot of the stuff in this space is. There's also these two books, which are very different. Some people may have heard of Nancy Leveson. She's well known in sort of the safety science world. Has been at MIT for a bazillion years. This is a really great book. It's not entirely about computing. It's about engineered systems in general. But she does talk a lot about the complexity that computing adds into these systems. And for that reason alone, it's very useful for us. Thinking in Systems by Donella Meadows is another classic text. She's more known for non-engineered systems. She was part of a very crazy project in the 70s, I think, called Limits to Growth, where people tried to model, how far can we take industrial society before it all falls down. It's not a happy picture. And unfortunately, it's proved more accurate than I would like. It's very interdisciplinary, is systems thinking. It's a hairball. It's everything from biology to maths to computing. Cybernetics and control theory, you may have heard of, they're part of it. Although, I mean, so is fish schools. We don't need to worry about that. The TLDR is that a system has elements or parts. So these could be, in our world, different services in a software system, or it could be, different processes working together in one service. It could be all sorts of different things. There have to be interactions and interconnections. This is where you end up with emergent properties of systems, so behaviors that were not necessarily designed in, but which can emerge. So things like oscillation. You may have seen this, if you have a microservice that has clients that do retries and you have a brief outage, all your clients retry, you have a drop in successful requests and then it goes up. And then if you're overwhelmed, you can have more errors and more oscillation. That's an example of an emergent property due to interactions in computer systems. So your body's a system, a school of fish is a system, a computer is a system, your Kubernetes cluster is a system. Systems are everywhere. It's the non-linearity of the interactions that make them hard. You can reach a tipping point. I think anyone who's ever done performance testing on a web service will have seen you get to a certain point and you have, X requests, 1,000 requests per second. You offer the load and the load responds, and then you kind of get a little plateau, and then it goes off a cliff because at that point your system is just churning and cannot handle the incoming queued requests. That's a non-linearity. You can respond to offer load and then you fall off a cliff. Interactions with the environment, service A gets slow because service B is slow. Service A runs out of sockets because service B got slow and now service A is on fire. All these kinds of things that we see. And our systems have state and history. But it gets worse. So when I came up sort of 10, 15 years ago, we would configure things by hand. We'd bring up systems and we'd run Puppet, and we thought we were great because we had Puppet and automation, and we didn't have to do everything by hand. And then you'd configure your new system in a load balancer, and off you go. We do not live in that world. We do not touch our systems. We build automation now that does this. This means that we're off at an increasing remove from our systems, and we've added a lot more complexity. So we are doing more difficult work now. We not only have to think about the system that's doing the work, serving your actual user requests, but you have to think about all the stuff we built around it. For good reason. We built it for good reason, but it adds a lot of complexity. So we haven't really thought about tools for how to deal with that cognitively. So the Handbook of Systems Thinking Methods, which I mentioned before, they did an experiment where they said, let's apply systems thinking to how to destroy the Death Star. And they did this method called work domain analysis, which comes from research that was done on nuclear reactors, only over the water in Denmark, in fact, by Rasmussen. So they took the Death Star plans, and they took some sets of students, and they trained them in these methods, and they set them loose on the Death Star plans. And they did a whole analysis on how to destroy the Death Star, and they did find the heat exhaust port. And they recommended fitting a grill. And they also found all these other things. Everything from sabotaging the medical droids to changing artificial gravity's direction, all sorts of things. There are applications of this if we want to understand how our systems can fail, which is, I think, a big part of your job if you are doing operations or reliability work. So these are the ways that I think we can use the systems thinking tools that Salmon and Stanton and so forth put out. So we can describe and understand our systems behavior, which gets us a long way, because I think when we're working with complex systems, onboarding and training new people in what's going on and getting people to sort of have common ground together about what's happening is actually a huge amount of work. We can use them to evaluate risk, and we can use them to analyze incidents that have happened. And I think all of these are important tasks. And we do a lot of this informally, with pre-mortems, tabletop scenarios, disaster testing, and incident reviews. But some of the formal systems that we could look at include these. So cognitive work analysis, like I say, this is from the Danish nuclear reactors. we look at what is the purpose of the system. We assess performance, which is like SLIs. And we look at what the functions and processes and so forth of everything are. We do a thing called control task analysis. So what tasks can be done in which situations? So what are the levers that we can pull? And I think in a lot of organizations, we don't really think about that until we find ourselves in a bad situation, and it does add time to recovery if you're interested in that. Hierarchical task analysis is a really interesting way of looking at systems as well. So basically, we take our system and we can decompose it into goals and sub-goals and operations and plans. It's really flexible. You can pretty much, I haven't found yet a system that you can't describe into it. And then we use that to do other kinds of analysis. So here's an example HTA. So let's say we want to reliably serve user requests. So we need to have enough capacity, and that means that we need to auto-scale, and so on and so forth. And then we need to do other things like alert if we don't have enough capacity, alert if we're serving 500s, and so on. Creating this kind of artifacts, I find it can surface things that we're not all aware of in a team. So it can surface gaps, it can surface kind of constraints, and it can surface sort of parts of systems like what does the rollouts, what are our health gates, all these kinds of things that we don't always talk or think about when we tend to focus, I think, on data plane requests, like a request comes in and is served here and blah, blah, and it goes out, but we don't think about all the stuff around that so much. I think socializing the knowledge of things like your rollouts, your credentials, so how does your MTLS shared secret work? How are your certs updated? How do backups work? How does resharding work? All these kinds of control plane things, I think, are often neglected. There's a thing called EastBL, which I forget what East stands for, but BL means broken links. It's really useful approach for when we want to figure out where can this thing fail. So you start with the horizontal task analysis that we just saw. Hierarchical task analysis. We create this network of tasks, and we look at what information is needed for each task to be done correctly and safely. So like, what are the feedback loops? And then we ask, what will happen if this link breaks? So take here that we have some sort of a distributed data store system of some kind. And if our system's disks are full, we need to reject writes. How can we plan to do that? What do we actually need in terms of information? And it turns out it's a lot, because this is a distributed system. So we need to know which machines are part of the system. We need to add up the reserved disk space for the file system, taking into account whatever other consumers of disk space there are, the operating system and so forth. Add up how much is used and compute the available. But all of these can go wrong in different ways. You can pick any box and say, what happens if this link breaks? So, for example, what if one of your machines starts reporting bananas results? One of the most entertaining incidents I've ever seen was a distributed file system where one of the machines basically had a bit flipped in their metrics and started reporting that it was using some insane amount of disk space, like petabytes on just this one machine, which was a lot at the time. And suddenly the whole system is like, I am rejecting writes because this is wrong. So then you can think about what you want to do in that case. So you could put reasonable limits and reject incoming metrics that are much larger than what any particular machine could have. So what's really interesting here is you don't have to justify how something will break. You just say, this will break, and then you can look at how robust the rest of your system is in response to that. I find this a really useful technique when you're reviewing any sort of a design. So, almost running out of time. Causal loop diagrams are very interesting. I like to use these to think about how volumes of work pan out in a system. So how can we avoid things like cascading failures and overload by putting controls in. But the models that we build, they don't need to be perfect. We don't need to model everything. We model the things that I think are considered risky and important. So our control processes, I think, for most of us. If you read Nancy Levison's book, Engineering a Safer World, her philosophy is all about thinking about what are the hazards that your system can encounter and what are the constraints and the controls and that prevent those hazards occurring. I think this is a very useful approach and not something that we talk about very much. I would like to see those become kind of first-class concepts in the work that we do. So to briefly sum up, there's a narrative that says we always have to be data-driven. I like data. Data is good. But I think we also need to think about what are the ways that we can use modeling to predict things that we don't have data on yet. Because I think that's part of engineering as well. We don't just try stuff and see what works. But also to sort of use that wisdom that we have gathered painfully over the decades. You've got to be flexible. We should skip over this with the SRE book. But what I'm saying here is, I think for those of us who are SREs or working in operations, I think the best of us are already using like systems thinking as a special sauce. I think this should be our North Star going forward as a profession. And we should make these kinds of concepts like the controls and the constraints, the plans, the links, and the tasks and processes, and the information that's being passed around in our control planes, sort of first-class things that we think about, not only the user-facing request flows that we always tend to focus on. Out with pillars, in with systems thinking. I'm talking tomorrow about something else completely. It will be about the work I'm doing about how people troubleshoot, how the mental models and thinking processes work when we're confronted with very, very difficult software incidents. And if you have any questions, I believe we're out of time, but you can contact me by these methods. Thank you so much.